Okay, welcome to lecture here. We'll get started in just a sec. Continuing on last chapter, kinetics. Okay, so we've been talking about kinetics, and we talked about sort of last time how to figure out the rate law. Remember that the rate law is really just the reactants involved. So it's like the rate equals K times the concentration of A to the X and let's say B to the Y. Again, unlike sort of a rate expression, the rate law only really deals with the reactants as they're involved in sort of the overall rate of a reaction. And remember that to determine the actual rate law of the orders, the rate constant value is typically found experimentally, which means, again, you're given a data table. And typically in that data table, you do have concentrations of all your reactants involved. You do also have the initial rates. And you can sort of mathematically determine those orders by choosing really two entries in that table. And usually that table, again, consists of multiple sort of experiments that were run for that particular reaction. And you want to choose really two entries in that table, as we talked about and as we did last time, where if there's only, say, two reactants involved, one of the concentrations of one reactant remains constant while the other one sort of varies. And the purpose of that is so you have really just one unknown. And you can do that rate 2 over rate 1 equals, the Ka to the X, B to the Y for both of those. As we talked about, a lot of times if you sort of put the one with the higher rate up on top all the way across, kind of the one with the lower rate all the way across, usually you'll end up with relatively whole numbers to sort of deal with at the end. And that's when you get to something like, say, 2 to the X equals 4 or something like that, where you can figure out that X is equal to 2 and something like that. You don't have to, again, necessarily put the one with the larger rate on top. You could do either one. It doesn't matter. Just the difference in that is you won't get necessarily a whole number, but you can solve it still mathematically doing something like taking the natural log of both sides and dividing. You can even take the regular log of both sides and divide. You can do both. And that will get you sort of your orders. In most cases, sort of book problems and things of that nature, usually they'll come out pretty close to whole numbers. They should. But if they don't, you can usually in that case sort of round if it's pretty close to the whole number for the orders. Once you sort of get the orders and you get the sort of completed rate law there, then you can actually solve for the value of K, which is the rate constant, or sort of how fast the reaction is sort of happening. And once you solve for K, to do that, you could go back to that table and again, choose any entry you like. It could be the first one, the second one, the third one, it doesn't really matter. You could choose any entry you like and put the numbers in. And once you do, you could actually get the value of K, the rate constant. As we sort of saw, depending on sort of the overall order of a reaction, which can be determined by adding up the individual orders like the X, Y, and maybe Z if you have a third one. The overall order of the reaction can be determined by doing so. And the value of K in terms of the units is really important because it does sort of tell you the type of reaction we're talking about in terms of whether it's perhaps first order, second order, zero order, and so forth. Any questions on that calculation stuff we did yesterday? Okay, so then we're going to kind of specifically talk about 3 different types of orders of reactions, sort of how they progress, what to look for to help you identify. It is, say, first order versus a second order reaction versus a zero order reaction. There also will be some equations, some concentration versus time type equations that are used specifically for different types of order reactions. So I think this is where we left off. So the first one we're going to talk about is a first order reaction. And in a first order reaction, we have A going to, say, product. And really, we write our rate expression here. We have the change in concentration of A over change in time, again, our negative. And if we turn that into our rate law here, the rate equals K to the A. And again, normally, like anything else in chemistry, you don't have to write the one, but with nothing there, it's implied to be first order and with respect to A. And this is important if we take this rate law and really solve for K. And if we solve for K and just look at the units associated with everything, K would equal the rate divided by the concentration of A. And the rate is typically molarity over seconds. The concentration is molarity. So when those do cancel, this gives us our very first sort of important information here, which is that the units associated with a first order rate constant is 1 over second or reciprocal seconds. And this is important a lot of times in kinetics type problems because they oftentimes will not just tell you, hey, it is a first order reaction with blinking lights. You know, they'll kind of give you the value of the rate constant. They'll give you the units associated with that rate constant. And you're supposed to know, oh, I see 1 over second. So that means that it is a first order reaction. I should use some of the first order equations we're going to see here in just a second. Now, although it is 1 over seconds, it doesn't necessarily have to always be seconds. It could be 1 over minutes, 1 over hours, 1 over weeks. It's really 1 over some unit of time is typically what the units are. Most commonly, though, thought of is 1 over seconds because if you just think about it logically, if you're doing some type of experiment in the laboratory, most likely it's probably going to be, seconds, maybe minutes in terms of how long the reaction will run for. We don't usually run reactions, for example, for days, weeks, and years. So usually the most common unit in terms of time is seconds a lot of times in kinetics. Otherwise, those studies would take forever. But it doesn't necessarily always have to be seconds. So again, 1 over seconds is most common, but it could be 1 over minutes, 1 over weeks, 1 over days, some type of unit like 1 over time. Now, there's what is sometimes referred to as integrated rate laws for these different types of orders. And there's two sort of graphs associated with a first order reaction. In a first order reaction, if you graph the concentration of A versus time, what we see here is our typical decrease with time, kind of going downwards. And another way that we could kind of take this sort of equation here, which relates first order, is to basically take the natural log all the way through it. And this right here is an important equation. This is the time and concentration dependence of each other. And that's the natural log of A equals the natural log of A naught minus KT. A is the kind of final concentration. A naught is the initial concentration. K is our rate constant. And T here is actually time, not temperature. So that's actually time, again, not temperature. And that's the equation for specifically a first order reaction. And first order reactions happen a lot. You'll see them again in 200B when you talk about nuclear chemistry. All radioactive decay follows first order kinetics. So all radioactive sort of decay of radioactive material will follow this sort of reaction order as to how they decrease with time, like we see on the left-hand side there. Now, if we take this sort of integrated rate law and just sort of rearrange it just a little bit, and we take the natural log of A equals minus KT plus the natural log of A naught. Now, this version of this equation, which is the same equation, just sort of rearranged, is in the form of a straight line. This is y is equal to mx plus b. which means typically when we talk about a first order plot, we usually look at the linear plot, and that means that on the y, we graph the natural log of A. On the x, we graph t, which is time. And what that will yield us, as you can see here, is a straight line. So we get this straight line, we're really with a negative slope. And the slope, as you can see here, is equal to negative k. And what that means is, since the line is negative, if you actually get the number for that line, it's going to be a negative value. The negative and the negative turns your rate constant into a positive number. And that's why it's equal to negative k. So usually when we sort of think about these different orders or reactions, we think about it in terms of linear sort of plots. And this one here is what you typically would plot for a first order reaction. There's also a half-life equation, which we'll see a little bit later on here, but the half-life is the natural log of 2 over k. And this equation, as we'll see and sort of talk about, half-life, much like the name implies, is the time it takes for half of whatever you have to basically go away. So again, if you started with 10, then after the first half-life you had 5, after a second you had 2.5, and so forth as you go through it. So in terms of importance on this slide, in terms of understanding a couple of things here. It's really important to know the units associated with the first order rate constant. It's important to know the integrated rate law here for first order. And also, as we'll see in a second here as well, the half-life equation. And although these are both technically first order plots, most people go with this graph here, the natural log of A versus time, which should give you that linear graph and that linear relationship as well. So those are sort of the important things there to make sure that you sort of know when you're dealing with sort of a first order reaction. All right. So here's again just another typical first order plot. And again, we see the natural log of the concentration of our reactant. So in this case is N2O5, gives us versus time there. And again, you can see it gives you a really nice linear fit in terms of the graph. And if you take your slope of that, again, it does equal minus k. So graphically, if you took the slope of this line, you could figure out the rate constant from it by, again, the change in the rise over run, which is your slope calculation. All right, so why don't you give this a try and see what you come up with here. So take a minute or two here. Reaction is first order with A, has a rate constant 2.8 times 10 to the minus 2. How long will it take for A to go from 0.88 to 0.14? So take a minute or two and see what you come up with. Okay, so let's take a look here. So this is this is first order, and it was easy to determine because they did tell us that. If they didn't actually tell us that, which is again very common that they will not, what we do have is the rate constant, which is K. And when we look at those units associated with K, we do see that kind of reciprocal seconds, or that 1/seconds, which again will tell you that it is first order. So again, that's why it's important to remember what those typical units are for K, because if they don't tell you, you'll be able to determine that it is first order. And why that's important is, although at this point we've only talked about sort of one set of formulas, it's important because you want to make sure you use the first order equation or formula for that, which is the natural log of A equals the natural log of A naught minus KT. Again here, A is our final concentration, which in this case is 0.14. A naught is our initial concentration, which in this case was 0.88. And obviously we have K given to us, which is our 2.8 times 10 to the minus 2 reciprocal seconds. So we have everything that we need really to kind of go into here. So the natural log of our final, which is 0.14, equals the natural log of our initial, 0.88, minus our 2.8 times 10 to the minus 2 reciprocal seconds, and T, which is what we're solving for. So when you do this, again, mathematically, there's a couple of ways, but probably the easiest thing just to do is kind of step by step. So if you take the natural log of 0.14 and then subtract it from the natural log of 0.88, as you would be subtracting the natural log of 0.88 to the other side. And then we want to divide by 2.8 exponent minus 2, going to give us something in the ballpark of about 66 seconds would be the units based off of here. So again, just to review, if you take the natural log of 0.14, you get something like minus 1.966 equals the natural log of 0.88, which is something like minus 0.1278 minus 2.8 times 10 to the minus 2. So again, subtracted this to this side and then divided by this guy. And again, that's how you got to 66. Any questions on that there? Also really important in this one and other sort of rate laws is these two guys here. And these two guys here, they do need to make sure that they are sort of in the same units. Again, sometimes the rate constant may be in, say, minutes, for example. Time may be in seconds. So you do want to watch out unit problems with those two because, again, sometimes they are in different units. If you do have to put the numbers in there, you do want to make sure, obviously, they're in the same unit of time. And that's a common place where people kind of mess up is they forget that they're in kind of two different units as well. Any questions on that there? Okay, so we sort of jumped on this a little bit earlier, but basically the half-life is the time as it requires for half of whatever you started with basically to sort of disappear. And after about 10 half-lives or so, it's probably pretty much gone and so forth. But to solve for the half-life, it basically means the initial divided by 2, which if you put that into our integrated rate law and solve for T, we get that half-life equation again for first order is the natural log of 2 divided by K. If you take the natural log of 2, that is where this number comes from. So if you take the natural log of 2 on your calculator, you get 0.693. So this equation here, the half-life equation and the sort of integrated rate law for our first order, these two equations are sometimes needed to be used together. And it's very common that these two equations are sometimes used sort of together in the same problem. And usually where that will occur is they give you the half-life of something, but they don't give you the rate constant. So a lot of times you'll come to this equation and go, okay, I'm looking for, say, that guy. I have this guy given to me. I have this guy given to me, but I don't have this given to me, but I am given the half-life. So a lot of times you will sometimes have to use the half-life equation to solve for the rate constant, then take the rate constant and actually put it into that integrated rate law there and solve for whatever you're looking for. So again, very common that those two sort of formulas are used together in kinetics. So why don't you try this one here? What is the half-life of N2O5 if it decomposes with a rate constant of 5.7 times 10 to the minus 4? Okay, so here we would use our half-life equation. Right, there we go. So our half-life would be, again, the natural log of 2 over k. And in this case, we do have k, so we just need to plug it in. Natural log of 2 over 5.7 times 10 to the minus 4 reciprocal seconds. And looks like we will end up with about 1,216 seconds, which is about 1,200 seconds on some significant figures based on this number, which has only 2 sig figs, give or take. And the second question there is, how do we know it's first order? Again, we know it's first order because of the units that we see associated here with the rate constant. Again, those units are reciprocal seconds or 1 over seconds, which again is your typical units associated with a first order reaction. Any questions on that there? So here's just a graphical representation of sort of the half-life. As you can see, if you count the green circles after the first half-life, we got half of those circles left. After the second half-life, we go from 8 to 4 circles, 4 circles to 2 circles. And again, typical first order is that kind of classic curvature as we start to decrease with time as it goes through. All right, so why don't you give this one a go? Reaction is first order with a rate constant. Find the concentration of SO2Cl2 at 865 seconds when the initial concentration is 0.0225. So see what you come up with. Okay, so let's take a look here. So same idea. Again, they were nice enough to tell us it's first order, but even if they didn't, looking at the units associated there with the rate constant, we do see that it is reciprocal seconds, which should point you in the direction of first order. And that would be, again, our natural log of A equals our natural log of A naught minus KT. So in this particular case, we are given K, we are given time, which is 865 seconds. We are given the initial concentration. So we are looking for our final concentration here. So we really have everything we need to plug into the right-hand side here. So that would give us the natural log of A equals the natural log of our initial, which was 0.0225, minus our K, which is 2.9 times 10 to the minus 4 reciprocal seconds, and our time, which was 865 seconds. So this is what I was talking about earlier, that again, if you are given these numbers, we do want to make sure that unit-wise, both of these guys are okay, and they are, because one is seconds and one is 1/seconds, which means they are going to cancel. But again, very commonly, these two guys in terms of their units of time are different. So you do want to watch out for that, because it is very common that sometimes will happen. So if we kind of clean up the right-hand side here by taking the natural log of 0.0225 minus 2.9 to, I scribbled on it, minus 4 times 865 gives us on the right-hand side, when we kind of clean up everything, minus 4.04508997-ish. Now, to get rid of the natural log on the left-hand side, you basically got to take on your calculator the E of both sides. So if you look on your calculator, you want to take the E of this, and that would equal the E of this as well. So you want to take the E of both of those sides. When you do that, on the left-hand side, it just becomes the concentration. The natural log basically cancels out. This we want to do, so usually on your calculator, again, above the natural log button is where you could find that. You want to take E of a minus 4.04, and that is going to give you a concentration of 0.0175 molar. And we do see it did go down, which is good, right? Because it should be decreasing with time. So our final concentration here is lower than our initial concentration, which would be good. Again, if you for some reason went the opposite way, that probably would not be so good if it went up instead of going down. Question on that. So again, E of both sides here, we'll do that for you. Any questions on that calculation? Okay, so in one more here in terms of first order, here we just want to calculate the half-life of this guy, so go for it. Okay, so on this one here, again, we're actually looking for the half-life, and looking at that rate constant there, the units tells us we do want to use the half-life equation for our first order, which is the natural log of 2 over K. And again, that's that 0.693 divided by 0.271 reciprocal seconds. And if we do that there, looks like 2.56 seconds. Again, these seconds go to the top when you divide, and that's how we get back to seconds in terms of that. That's pretty quick. That means pretty much every 2.5 seconds, half of this goes away. So, you know, within like 20 seconds, you know, you probably have almost all of it kind of gone. It goes very, very quickly in terms of this reaction. Any question on first order reactions? So first order reactions, again, typically like a decomposition type reaction where, you know, we have one reactant that's basically decomposing. That's usually sort of your first order type of equations. All right, so let's take a look at another type of order, which is second order. Now, second order could be one of two sort of situations. You could have, again, one reactant that decomposes at sort of a second order rate. And you could potentially have two reactants where they both are first order. And when you add that together, obviously 1 and 1 will give you 2 or second order. So you could have two reactants that are sort of reacting with each other, sort of in a one-to-one sort of relationship. Or again, you could have sort of that one reactant that's decaying. So if we look at the rate law here, the rate is equal to K times A to the 2, which means, again, it's second order. And just like in first order, if we look at the actual units associated there with a second order reaction, we see a different set of units that typically comes about in a second order reaction. So in a second order reaction, we see 1 over molar seconds. And much like first order, it's also the same idea with the time part of it. Doesn't necessarily have to be 1 over molar seconds. It could be like 1 over molar minutes, but it's basically 1 over molar, some unit of time. And if you see those units associated with a K value that's given to you, you know that it is a second order reaction. And with that, that means that it actually has its own set of sort of time and concentration dependencies in terms of an equation. And this is our second order reaction, sort of our integrated rate law here. And is 1 over A equals 1 over A naught plus KT. These are all the same information as it was in the first order. This again is our final concentration. This is our initial concentration. This is our rate constant, and that is again still time. Now, also different than that is if you substitute in 1 over A for 1 over A initial divided by 2, we do get a half-life equation for a second order reaction. And it also is different than the first order one. It is 1 over K times the initial concentration. So unlike first order, where the half-life is not affected by how much your initial concentration is, because it's the natural log of 2 divided by K, it's just a rate constant, or how fast the reaction is happening. Here in a second order reaction, the half-life is affected by the initial concentration. So 1 over K times the initial concentration. So the higher the initial concentration, right, the smaller the half-life will be. And again, the smaller it will be, the kind of larger the half-life will be in there. Now, if we take this guy as well, just like what we did with the first order one, if we take our 1 over A equals, not that, one over A and then equals, we kind of do a little rearranging, KT plus 1 over A naught. This is the second order equation written in the form of a straight line. This is Y is equal to mx plus b. And this helps us understand the graph that we typically see for a second order. On the Y is 1 over A, and on the X is our T. And unlike a first order sort of graph, this also gives us a linear line, but it's actually a positive slope happening there. And that means that the slope here would equal the K value. So graphically here, again, if it's second order, you could do a graph. You could figure out the slope value and can also figure out what the value of K would be in that case, just from the graph. So much like first order, in terms of second order importance here off of this slide, is all kind of the same stuff in that sense. It's important to know the units associated there with the rate constant. So that will point you to the right one, which is your second order. Important to know the time and concentration of a second order reaction, and also the half-life, and again, the graph that's typically associated there with your second order one. So again, a little bit different, a positive slope line here happening in this particular graph. Now, the last type of sort of reaction we're going to talk about in terms of orders is a zero order reaction. And a zero order reaction is usually when you have perhaps one reactant and it's to the zero order. So when you take anything to the zero order, like here, take something to the zero, it does equal 1. And that means that when we solve for K here, basically the units associated with a zero order reaction is molarity over seconds. It's the same units that's associated with the rate constant, I'm sorry, the rate, which is molarity over seconds. And we also have an integrated rate law, which looks just like first order, except no natural log. So this is the one that is for zero order. And we also have a half-life here, which is the initial concentration divided by 2K. Here, again, the initial concentration is important in terms of the half-life that we see. Here it's on top, right? Which means, again, the larger the initial concentration, the sort of smaller the half-life, the smaller the initial concentration, sort of the quicker the half-life would be. So this, again, is concentration dependent on that. Much like all the other two there, if we do a little rearrangement of our rate law here, we get this, and this again is our y is equal to mx plus b, which gives us the typical graph that we see for a zero order. On the y is the concentration, on the x is the t. And you may say to yourself, I think I've seen this graph, and you did. This graph is the same thing that's being graphed on a first order as it is a zero order. But the difference is here, when you do a zero order graph, you actually do get a straight line where the slope equals minus k. If you remember on our first order, if you did that same graph, the concentration versus time, you do not get a straight line. You get this decreasing over time type of curve. So sometimes people still look at this graph for first order concentration versus time, but usually concentration versus time, if it yields you a linear line, a perfect kind of straight line, that would mean that it is a zero order reaction taking place. If you do a concentration versus time, you get this sort of decrease over time, this kind of curvature line, that usually would mean it is more first order. So again, they are technically kind of the same graphs that are being used, but they do give you a different result depending on if it's first order or zero order. Again, zero order here will give you a linear fit when you do concentration versus time. First order will not give you that linear fit. So just like the other ones, units, equations, and graph is typically, again, the important things here off of this sort of slide. Okay, so why don't you try one here and see? The reaction is second order with K if the initial concentration is 0.01, and after 500 seconds is 0.001. What is the rate constant? So see what you come up with on this one here. Take a minute or two. Okay, so let's take a look. So here they obviously tell you the second order. Since we're looking to find the rate constant, obviously we can't use the units associated with it. But that does important because it means we should be using the second order formula here. 1 over A equals 1 over A naught. This is actually plus KT. In this particular case, we have everything except for K, which is what we're looking for here. So our final concentration after 500 seconds is 1 over 0.001 equals our initial concentration, which would be 1 over 0.01 plus K, which is what we're looking for. And our time here is 500 seconds. So again, mathematically here, I will take 1 divided by 0.001, it equals. I then will subtract 1 divided by 0.01, it equals. And if you do that, it looks like 900 happens over here, equals K times 500. We're then going to divide the 500 to the other side, and we are going to get a K of 1.8. Now, unit-wise, I didn't write them here, but that's molarity, that's molarity. And when we subtract those guys, we still have basically 1 over molarity. Then when we divide the seconds here, we get 1 over molar seconds. And again, you could write it like that. You could write 1.8 minus 1, s to the minus 1 is perfectly fine as well. And if you look at this, these are the typical units that we see associated with a second order reaction. So that's a good way to sort of check yourself. Again, as we sort of talked about, first order in K is 1 over seconds. That's like 1 unit. Second order is 1 over molar seconds. That's, 2 units, right? And zero order is the only one where, you have molarity over seconds, which is 2. But, it's a good way to sort of figure it out other than zero order. You can kind of figure out how many units you got going on there. Okay, so we got that. Any questions on that calculation there? Okay. So here's a nice little table of really the sort of important information in terms of concentration versus time equations and the different orders and the half-life equations. So again, oftentimes these will have to be used together, the half-life and the concentration versus time one. But sometimes you don't have to, but sometimes you do need to. So that's a good little slide there to sort of know, at least the last 2 columns of the slide. And, you can, if you're sort of doing an experiment, for example, use the graphical way of determining the order by doing those different graphs. And that's why the graphs are really important to understand which one goes with which in terms of what is being graphed. So sometimes, and it's an experiment that's sometimes done, and I teach a class where they do that. They basically are trying to figure out the order of a reaction. So basically what they do is they do the experiment, they get the concentration, they get the time that's happening, how the concentration is changing with time. And essentially, in order to figure out the order of the reaction, you make all 3 plots. So again, if you plot your concentration versus time and you get a straight line, that's going to tell you it is 0 order. If you plot the natural log of A versus time and you get a straight line, that again will tell you it's first order. And if you plot 1 over the concentration versus time and you get a straight line going again in the positive direction, that will tell you it's second order. Now you potentially could get a almost linear line for each of those. And the way you sort of determine sort of what the order would be, if they all sort of give you a linear-ish line, is if you use something like Excel, for example, you could use the R² value, and that's the linear coefficient. And an R² value of 1 means that it's like perfectly linear. You got a nice perfect straight line happening. And that's sometimes how people, when they sort of use the graphical approach, they look at the graphs that they did for each of these guys. They do that best fit line. They get the linear regression. and they look at the R² value. And the one that has an R² value closest to 1 would be the most linear and would also tell you the order of that particular reaction, you know, through graphical sort of purposes. Any questions on that there? So what we're going to talk about then is the relationship between temperature and sort of the rate and what happens with that. And the first thing here is these are two graphs. Good talk. Go back. These are two energy diagrams. And the one on the left is an exothermic diagram. The one on the right is an endothermic diagram. A reminder that exothermic means heat and energy is absorbed. That is not what it means. It means heat and energy is released when we say that, right? So heat and energy is released for exothermic, and endothermic means heat and energy is absorbed. And usually, as we talked a little bit about this semester, that, and again, you'll talk more about next semester, but when we talk about energy, exothermic, endothermic, usually we look at delta H, which is the enthalpy, and the enthalpy value is negative for an exothermic reaction. Delta H is positive value for an endothermic reaction. So when we look at this energy diagram on the left, this is our reactants, these are our products, and what we see is our reactants are higher in energy than our products. And that usually means in order for those reactants to get down to the energy of our products, energy has to be given off, which means it's an exothermic. And that's opposite of what we see in an endothermic reaction. In an endothermic reaction, our reactants are lower in energy than our products. So in order for our reactants to get up there in energy, energy has to be put in or absorbed. And that's really how, when you look at sort of an energy diagram like this, you can determine whether or not it is exothermic or endothermic is by sort of the placement of the reactants versus the products. Now, as a reaction proceeds, what basically has to happen is a couple of things, right? They need to, sort of collision theory, everybody needs to kind of come in contact with each other. So the reactant molecules need to come in contact with each other. And they really need two things to happen when they do that. They do need to hit each other sort of in the right location, sort of the active side, if you will. And they also need to hit each other with the minimum amount of energy required to sort of start that reaction. So not all collisions when two molecules come together will result in a product being formed. Products will only be formed when that sort of two things happen. They hit each other sort of in the right location, and they also sort of collide with each other with the right amount of energy to do that. And when that occurs, that sort of right amount of energy, or that hill is sometimes described that the reactants has to climb to get to the other side. That is what is known as the activation energy, which is the E of A. So the activation energy is really the minimum amount of energy that's required for a reaction to occur. Again, as you can see it here, is really that energy hill that the reactants has to climb as they are breaking bonds and coming to the other side and making new bonds. So this little part here, from where the reactants start in energy to really the top of the hill here, that is our activation energy. Same thing here, sort of where the reactants start to the top of the hill there is our activation energy on the endothermic reaction. And as it proceeds, as those reactants proceed from left to right in that reaction, we're starting to make bonds, starting to break bonds, and then starting to make bonds. And when we get to the very top of the hill there, that top of the hill is what is referred to as the transition state. And this little guy here that has that little symbol right here, this is what is sometimes referred to as a transition state complex or an activated complex. And a couple of things about that guy there is, if you see his location on really both diagrams here, that transition state complex or that activated complex is at the top of the hill, basically the highest point in energy that you could have in this process. And one thing that you hopefully should have got from this semester is in terms of energy. When things are in higher states of energy, they're not very happy. So things don't really like to be in high states of energy. Stability really occurs when things are sort of in their lowest states of energy. So something that is right there at the peak of highness in terms of energy is something that's very sort of unstable, if you will. It's something that does not hang around a very long time. And what usually ends up happening is it very quickly will drop down to the other side to make products. That's why transition state complexes or activated complexes, they're very hard to usually isolate because they're so unstable. They very quickly kind of disappear. And that's because really, as we'll talk about in a second as well, this guy here, it's really a substance that has sort of partially broken bonds and partially bonds that are being made. So it's this sort of substance that has partially made, partially broken bonds, makes it very reactive and not very stable, going to hang around a long time. Again, you can kind of picture it here as it's sort of progressing this way. We're starting to break bonds. We're also starting to make some new bonds. So by the time it gets to that peak at the top, it's got some partially broken bonds, some partially made bonds, and then very quickly it will kind of drop to the other side and again make those new bonds. The other thing that we can also see here is a couple of things. We do see that the hill for a exothermic process looks much smaller than the activation energy for an endothermic process. That also makes sense if you think about what those two definitions mean. Exothermic means it's got some excess energy, if you will, to be able to give it off. So the hill is not so big to get to the other side. Endothermic process means you got to put some heat and energy in there to help everybody get up and over to the other side. How does this affect the rate of a reaction? Well, the bigger the activation energy, the bigger the hill to get to the other side, the slower the reaction is going to occur, because it's going to take a lot longer for those guys to get up and over to the other side. It's like if you had to walk a big giant hill, it's going to take you a lot longer to get to the top and then down the hill the other side than if you had just like a little kind of bump or something like that in terms of a hill. You'll get to the other side much, much quicker. So how does temperature relate to this? Well, temperature relates to this, obviously, as we will see, that if I increase the temperature, I'm probably going to have more molecules that have enough energy to get up and over to the other side. While if I lower the temperature, everybody's going to lose some energy, they're going to move slower. There's going to be less amount of molecules that again can get up and over to the other side, thus slowing down the reaction. And that relationship that we see between temperature and sort of the rate of the reaction is what is known as the Arrhenius equation, that we sort of see a version of it here. And we'll talk about some of these other things here, but R is our gas constant, is actually the one that involves energy here. A is the frequency factor, and as we'll talk about, as sort of the proportional molecules that have sufficient energy to get to the other side. And E of A here, which I can't see on my screen, but I think that says activation energy there. Again, is that energy that's really needed, that minimum energy to start the reaction. And again, that's what we kind of see here. Here we have our reactants, our products are lower in energy. This is an exothermic process. And again, as this process proceeds, these guys are going to break apart. These guys are going to start to break apart. They're going to start to break apart. But then they're going to start to form some new sort of bonds as well as they move towards that transition state again, and then very quickly sort of drop down to the other side. So that energy barrier for all reactions is what again is known as that activation energy. At the very top of that, as I mentioned, is a activated complex, again sometimes referred to as a transition state complex. And that transition state complex, or that activated complex, is a species, as I said, that has that sort of partially made bonds, partially broken bonds. It makes it very high in energy because of that. And again, very quick to react because it wants to sort of complete the transition, if you will. It doesn't want to stay in that high energy and not really complete that transition. So if we sort of graph the relationship between the rate constant and temperature, We could take a look at that here. And if we take a look at it, we see what we've been talking about, that if we lower the temperature here, the rate constant is smaller. If we start to increase the temperature, the rate constant, or the sort of speed of the reaction, will start to increase. And again, that's really for what I just mentioned, that as we increase the temperature, we're getting more energy involved. More energy involved means there's going to be a greater amount of molecules that will have that sufficient amount of energy to basically hop over the hill. Now, if we take the Arrhenius equation, which is up here, and basically kind of integrate it with the natural log all the way across, we get this version of the Arrhenius equation. And this version is oftentimes used for graphing purposes and to sort of graphically determine things like activation energy. And that's because this is written in the form of a straight line. This is y is equal to mx plus b. And that's not the graph that we see here. But if we do that graph, what we will end up with is a graph of the natural log of k on the y. On the x, as you can see, is 1 over the temperature in Kelvin. And this will yield you a straight line, as best I could draw it. And the importance of the straight line when you're sort of doing this graphical approach using this equation here is that if you take the slope of the line, it equals this here. So from the slope, it would equal minus E of A over R. And that basically means to find the activation energy, you just need to multiply by the 8.314 to the other side. Now, this line here, as you can see, has a negative slope, which means the negative here from the slope value, and this negative will turn your activation energy into a positive number. And that typically is what an activation energy should be, is a positive number. That negative and negative will take care of that. So this is a very common sort of equation. It's a very common process that's done to figure out the activation energy of a reaction, again, through sort of graphical way of doing that. And here is a graph of that. And again, you can see you get a very nice straight line where, again, if we took the slope of that line, it would minus E of A over R, again, multiplying by R, and the negative gives you your activation energy. The other important thing that we could actually get from this sort of graph as well is the y-intercept. So that is y is equal to mx plus b. So where we see the y-intercept, wherever it would be, back this way, if we follow that line, that y-intercept would equal the natural log of A. So this gives us a way to figure out what A is. And again, A is the frequency factor. And for basically what it is the proportion of molecules, again, that have enough energy to get up and over that hill. So that's sort of the frequency factor, that fraction of molecules that have that sufficient amount of energy basically to get to the other side. So those are two common things that people sort of get from this sort of Arrhenius graph here using that formula. And here again is some of the things that we talked about. Again, that fraction of molecules with sufficient energy to get up and over that energy barrier. The higher the energy barrier, the larger the activation energy, and there's less molecules that have enough energy to overcome it. Again, increasing the temperature supplies some extra energy that's going to allow normally guys that won't have enough energy to get over enough energy to get up and over. And again, ultimately, that's why when we talk about we increase the temperature of a reaction, the rate of that reaction increases. Again, ultimately, we're just supplying more energy, going to allow more people to get over that hill, reaction to occur a lot faster. And obviously, the opposite is true. Again, if you took everything, you put it on ice, and you kind of cooled down the reaction, did it at a much lower temperature, you're basically removing all that energy. And that energy that's going to be lost is going to cause the number of molecules with enough energy to get up and over to really start to decrease. And as that number decreases, the rate of the reaction will slow down. again, because there's less guys that have enough energy to get over, because you kind of drove out all the energy from that particular reaction. And that's what we see here in this particular graph. These are the same sort of reaction done at two different temperatures. Temperature 2 here is higher than temperature 1, and this is the activation sort of energy. What we see is in the first temperature, there's only about this much molecules that can get up and over to the other side. When we look at it, what happens when we raise the temperature, now at that same spot, we have, you know, a whole bunch more molecules that have enough energy basically to get to the other side. So you can see here just graphically, by increasing that energy, we do increase the amount of reactants or molecules that could get to the other side. In case you missed this equation the first 7 times we saw it, here it is one more time. So let's take a look at a problem here where typically you'd make this type of graph, and this is typically the sort of the information that you would be given. I obviously wouldn't anticipate you graphing anything on a test in here, but maybe in the book problem or something like that, you would have to make a graph. But basically you'll be given either the temperature. A lot of times you may be given the temperature in Celsius, so you do need to convert it to Kelvin if it's not in Celsius. Again, it does need to be Kelvin here for the temperature. Happens to already be converted for us. You do typically would be given the rate constant at each of those temperatures. And basically here we would want to make that plot, which means for our temperature, we need to take all the temperatures and do 1 over the temperature. And for our Ks, we would need to turn all those into the natural log of Ks. So for both of these columns, we would change them into these guys. And that would then provide the information we need to actually do the plot of our natural log of K versus 1 over the temperature, which again should yield us a straight line. So typically you'll be given some type of table like this. You have to do a little bit of manipulation. And if you do that and do a graph, you get something that looks like this. Again, the typical Arrhenius plot here, our natural log of K versus 1 over the temperature. As you can see here, yields are straight line. This is our y equals mx plus b. So we could use this information here to solve for what it asked us for, and it asked us to solve for the activation energy and the frequency factor, which again is that A value in that equation. So if we take a look at it here, looking at our original sort of equation here, natural log of K equals minus E of A over R, 1 over T plus the natural log of A. So remember, this is our y is equal to mx plus b. So taking the equation that they gave us in that thing, it was y is equal to minus 1.12 times 10 to the 4 x plus 26.8, I believe, if I'm not mistaken here. Make sure I got that right. 1 to the 4, right? Yeah. Okay. So when we look at this, this obviously is our y equals mx plus b. So remember that the slope, when you do this, is equal to minus E of A over R. So our E of A would equal minus R times the slope. So again, minus our 8.314, which is our gas constant. So that's that constant value. The slope is going to come from the equation from the line, which is right here. And that would be minus 1.12 times 10 to the 4. Again, as we talked about, our negative here and our negative here, it's going to turn our activation energy into a positive number, which is what we want. So we take 8.314 times 1.12 to the 4th. Going to give us an E of A of 93116.8. The units here are actually joules per mole. So this is joules per mole, which again, activation energy is usually given in kilojoules. So we could divide that by 1,000 and we get something like 93.1 kilojoules as our activation energy. Again, a positive number, which is what we would expect. And again, that represents the energy to get up and over the hill from the reactants to the products in this particular case. Now, the other thing that it asks for is the frequency factor, which is A. And again, the natural log of A is equal to the y-intercept. So the natural log of A equals B. Again, B here from our equation from our graph is 26.8. That means that the natural log of A is equal to 26.8. To get rid of the natural log, we're going to take the E of both sides. And again, when we do the E of the side on the left, it just becomes A. And if we take the E of that guy, gives us something like 4.36 times 10 to the 11. Now, the units of this actually will become the same units associated with the rate constant. And I'll show you why that is in just a second here. So basically, the y-intercept means that we are talking about crossing the y-axis, which is the natural log of k. Now, when we take the e of that, we're basically taking it back to k. And if you go back to the units associated with k, those are where the units come from. So typically speaking, when you sort of figure out the frequency factor, they typically will end up with the same units as the rate constant had because of that, because it's basically the y-intercept and, you know, it's basically derived from the rate constant. So that's how we get sort of the units associated with that. And again, this is basically the proportion of molecules that have sort of the sufficient amount of energy to get up and over to the other side there. Any questions on how to graphically determine the activation energy? So obviously, I wouldn't anticipate you having to graph anything, obviously, or anything like that. But if a graph was provided for you, you should know how to use it to determine things like the activation energy or the frequency factor. Any questions on that? All right. So people don't like to make graphs usually, right? So there is a way that we can sort of mathematically determine things like activation energy, temperature, and this is also the Arrhenius equation. This is more of the non-graphical approach to it, sometimes referred to as the two-point version of it. And really, you just need information about 2 points along that line. And really, it is based off of that line we just saw. But really, you just sort of need information maybe about 2 points on there. And you could kind of use this sort of mathematical approach to do this. Now, there's a few different versions of this equation that you see. So this is one legitimate version. This is the natural log of K2 over K1. So that's the rate constant at one temperature, the rate constant at another temperature. That equals E of A, which is our activation energy, just like we had before. This is our R, which is still our 8.314. It's our activation energy. It's our rate constants. And T is our temperature here in Kelvin, right? So our T is here is our temperature in Kelvin. So we can use this and sort of mathematically solve for something by just basically substituting it into here. So why don't we try one here and see how you do. So take a shot at this one here. The reaction of there, it has a rate constant 2.5 at 701 Kelvin and 567 at 895 Kelvin. Find the activation energy. So take a minute or two to see what you come up with. Okay, so we're getting to the end here. Let's take a look. So we're finding activation energy, and again, we're obviously not going to do the graphing version of it. So we're going to take our equation, which is the natural log of K2 over K1 equals E of A over R 1 over T1 minus 1 over T2. So we have some information given to us, and it doesn't really matter which one you sort of pick as 1 or 2, as long as you kind of keep the information that goes together. So for example, if we just kind of roll through here and go, okay, that's going to be our K1 is 2.57. And since that's our K1, our T1 that should go with it is 701. It's already converted to Kelvin for us, so that's good. So we don't have to worry about it. That would mean that my K2 would be our 567. And because that's obviously our K2, the temperature that goes with that should be our T2, which is 895. So we have pretty much everything we need to kind of plug into here. We got the natural log of a K2, which is going to be 567 divided by K1, which is 2.57, equals E of A, which is what we're looking for, 8.314, which is our gas constant. 1 over T1, which again, already in Kelvin, if it wasn't, you do need to convert it, minus 1 over T2, also in Kelvin. And again, if it was not, you do need to do a little conversion there. So if we do a little bit of cleaning up over here, we'll start on the left-hand side, 567. You want to actually divide it first and then take the natural log of it. And that gives us something like 5.3964 equals our E of A over 8.314. And if we clean up what's in our parentheses here, 1 divided by 701 minus 1 divided by 895 gives us 0.000392. At this point, we're going to multiply the 8.314 to the other side. We're also going to divide by that number we just got. And that means that we will take our 5.396 times 8.314 divided by 0.000392 gives us 145,103.9. equals our E of A. Units here would be joules based off of this number. So it would be joules per mole. Again, activation energy typically in kilojoules. So you can divide it by 1,000 and get something like 145 kilojoules per mole in this particular case. Now, when we do use this equation, a couple of things unit-wise, these two guys here, you do need to watch out for. Again, if you are given the activation energy, it is typically in kilojoules and R is in joules. So again, you typically will have kilojoules on top and joules on the bottom. So you do need to do a conversion there. Otherwise, you're going to be off by a factor of 1,000. So that's a common place where people kind of mess up, is they don't watch those units that are right there. Any questions on that there? Okay, so I think we will stop here. And we'll go to lab in about 20 minutes or so. And we'll talk about the very last experiment, which is a kinetics experiment. And I think we may just kind of finish up this stuff here and just be done with it, I think. Any questions on any of that there? Okay, I'll see everybody in about 20 minutes. Make sure you're right here if you haven't done so already. And we'll start about 9:45-ish there for lab.